So I'm doing a short video today about Gabriel's horn. I'm not going to subject you to my trumpet playing, but because I really can't. But I am holding this old broken trumpet that used to belong to my son because it illustrates the shape we're trying to get. Right, the bell of the trumpet is some surface of revolution, obviously. In fact, it's not 1 over x, but the version of things we're going to use is the outer profile of the horn is 1 over x. And you know, the reason I think the trumpet is kind of an interesting object, but the tube has been rolled up multiple times. This thing actually goes around and around before it goes to from the mouthpiece. So if you straighten that trumpet out, it'd probably be about 5 feet long. So anyway, that's the shape we're considering. It looks like the graph of 1 over x, but then spun around the y-axis. Now we're going to just do the part of it that goes from 1, 1 off towards infinity, 0. But that graph, try to be as careful as I can. It gets closer and closer and closer to the x-axis, becoming almost indistinguishable fairly soon. And we're rotating this graph around the x-axis. Right? So this is the graph of y equals 1 over x, spun around the y-axis. If I draw it in sort of perspective nearby, it would look more or less like this. An infinitely long and infinitely narrow trumpet bell. Okay, center line going like in the middle. Now, there's the amazing thing about this so-called Gabriel's horn, which I love the name, is that it's got a finite volume. The volume of this object, and in fact the volume is pi. So if you had, I can't seem to spell, volume equals pi. If you had pi gallons of paint, you could turn this thing 90 degrees and pour it in there. It would fill it up. But its surface area is infinity. Which is a real mind bender, right? The idea that it could hold a finite amount of paint, but that finite amount of paint could never be used to paint it. And yet if you poured that amount of paint in there, it would seem like it would paint the inside surface at least. But yeah, that's the twist about this object. Now we're principally doing this, or looking at this as an example of an improper integral. So let's mention just the general thing, that if you have an integral that goes from some point A to infinity of a function, we just define that integral that has an infinite limit in the sense of the upper end of the integral, to be a limit in the other sense of the word limit. I always have a hard time getting the correct number of humps on my m's when I'm doing the word lim. Anyway, the limit as b goes to infinity of the integral from a to b of f of x dx. All right, so we're going to use this definition of what's the meaning of an improper integral to figure out both the volume and the surface area for Gabriel's horn. And actually, I think in our video live feed on WebEx the other day, we did this part, and then I got stuck on the surface area. I looked it up, I cheated, and figured out how to present to you the idea that the surface area is infinite. But I wanted this video to be self-contained, so I'm going to go over the volume again, and then we'll look at why the surface area is infinite. Right, so let me scrape away this part, and we'll keep the picture of what Gabriel's horn looks like, or at least the schematic of it. At some point in the midst of it, you think about a cross-section of that. And that cross-section corresponds to a disk, so I'm using the disk method to think about the volume. So what kind of dimensions does this disk have? Well, its radius is the y-coordinate on the curve, right? So our radius equals 1 over x, and our thickness, that guy, that's we're integrating in the x direction, right? From x equals 1 to infinity. So that's a little bit of differential length in the same direction as x. That's dx, which means the differential volume for that chunk of our volume is pi times the radius squared dx, or pi 1 over x quantity squared dx, right? And that means the volume of our horn, the surface of revolution, is the integral from 1 to infinity of, let me pull the pi out front, 1 over x squared dx. Okay, so that's the calculus-friendly way to talk about it is that's x to the minus 2 power. When you add 1 to minus 2, you get minus 1. And so an antiderivative is x to the minus negative of x to the minus 1. In other words, negative 1 over x. Right? We got that multiple of pi out front, and we have to think about limits going from 1 to infinity. Whoops. Well, for that, we're going to use the limit trick. Okay, so we'll take the limit as b goes to infinity of, well, actually, you know what? We can get that pi out of the limit as well as out of the integral. Negative 1 over b, that's the upper limit, minus negative 1 over 1. Right. Well, that's a limit we can actually evaluate. As b goes to infinity, this term goes to 0. Negative 0, I guess. But this term has 2 minus signs in it, so it's 1. So this limit is actually just 1. So what do we get for the volume? Like I said before, pi. Finite amount of volume. Now let's take a look at the surface area. Now, I was creating a little visual aid to help you think about the surface area. So hopefully I can make this work again. Sorry. The surface area is really the outside part of a frustum of a cone, right? So just tape it in place on the thing. It's got a little bit of length that way, and then it's spun around the circumference of any one of the discs that we were talking about in the disk method. So, yeah, let's think about that surface area. Here's one of those objects kind of pulled loose. It's got a width in this direction that's differential arc length along the curve, and it's got a length in that direction that's the circumference of our curve. So to talk about arc length, we need to think about ds, the differential. Sorry, to talk about surface area, we need to think about what is ds. Well, remember the general formula for that. It's square root of 1 plus the derivative of your function squared dx. And for us, our y was 1 over x, so y prime is, that's like x to the minus 1 power. Subtracting 1 from the power, you get minus 2 power. Put a minus 1 out front, 1 over x squared. Negative 1 over x squared. So that's what goes into where y prime is. Okay? That means this differential arc length is square root of 1 plus 1 over x to the 4th power dx. Now that's arc length. To get the surface area, the part that's on the outside of this frustum of a cone, what should we call that number? I'm going to use little a because I usually think of big A as area, but this is surface area. Well, okay. It'll be the circumference, 2 pi r, the radius of a, no, it's really a frustum of a cone that we're looking at in there. Whoop, bad sketching. But, you know, physically it's right here. The radius of that thing is 1 over x. So 2 pi r is 2 pi times 1 over x. And the width of this little strip of paper is ds. Okay. Now, I believe I got this far in class before. We just need to move this 1 over x under the radical to take something that's outside of a square root and put it inside. You need to square things so that you don't change it. You do need to worry about you're not introducing something negative under the radical, but we're dealing with x values that are 1 and larger, so that's not an issue. Okay, so we get 2 pi square root of 1 over x squared times that other stuff, 1 plus 1 over x to the 4th, and then dx. And finally, just multiplying it in, this is 2 pi square root of 1 over x squared plus 1 over x to the 6th dx. So we would integrate that with the limits 1 to infinity in order to figure out the surface area of Gabriel's horn. So let me set up the integral we need to do. That surface area is equal to the integral from 1 to infinity of the integrand I just wrote down. 2 times pi times the square root of 1 over x squared plus 1 over x to the 6th dx. And here's where I kind of went wrong. This would be a pain in the neck to integrate. I'm not sure that it would ever be possible. But it is possible to just estimate. What I'm really interested in doing is showing that the surface area is infinite. So I'm gonna cheat a little bit and show you a different integral that I know is infinite, but that is smaller than this one. So if this thing has got to be bigger than something that's already infinite, it's going to be infinite. So what do I want to show you? I want us to notice that the integrand we've got there, 1 over x squared plus 1 over x to the 6th, square root of that quantity rather, is strictly bigger than 1 over x. And that's because, well, let's see why this is true. But we are dealing with positive values for x, so these things are both positive under there. Why? Well, first off, you'd say, okay, 1 over x squared is square root of 1 over x squared. That's equal to 1 over x, isn't it? If we just square both sides, I'll get that 1 over x squared is equal to 1 over x squared. Sure, that's a silly thing to even write down. Now, what I'm going to do is add something that's positive to this side, and that will turn it into an inequality. And something I'm going to add to this side is 1 over x to the 6th. So because those things are equal, this is now bigger. The left side is now bigger than the right side. Take the square root of both sides and you get the thing I said originally. Okay. So why is that going to be handy? That means that this integral we've said for the surface area is actually larger than the integral of 1 over x. At every x coordinate, this side thing is bigger than that thing, so when I integrate, I'll definitely get something larger. There is a slight amount of me playing fast and loose with limit laws here, but what is actually, what I'm saying is actually true, but it does need to be justified carefully by thinking about limits. All right, so that means this integral is actually larger than the integral from 1 to infinity of 1 over x. And we'll be done then if I can show you that this integral is infinite, right? Great, so let me take a second and scrub the board. But let's leave this part that's at the top so we can see where we're heading. I want to show that 1 over x integrated from 1 to infinity is infinite. So that integral, 1 to infinity of 1 over x dx, that's equal to the limit with b going to infinity of the integral that just goes from 1 to b, 1 over x dx. And 1 over x has an antiderivative. Its antiderivative is a log of absolute b. All of our values, both for the low end and the high end, are positive, so I can just write natural log of b minus natural log of 1. Whoops, I forgot to leave the words limit up front here. Right. So natural log of 1 is 0, and so this is just the natural log of b. And there is no finite number that is a cap on the natural log. That is, as I let b go to infinity, natural log of b can get as large as you want. In particular, if you have some idea in mind that this maybe is approaching a horizontal asymptote, I can disprove that for you. Suppose that thing was reaching some level L. Well, take e to the L power and you'll find the place where natural log first exceeds that. So this is infinite. And that means this integral is infinite, and the one we're really after is bigger than that. So, boom. Surface area is infinite, yet the volume is finite. In fact, the volume was pi, not even a very large number. So that's Gabriel's horn. It's really kind of a mind blower.